Welcome everyone to the Berlin Functional Programming Group once again. Tonight I'm pleased to welcome my friend John DeGoes. I met John at his conference LambdaConf, I think in 2015, and I've attended 3 times. Sadly, not since 2018, but I'm hoping I can attend again once this pandemic is over. It's a really great event, and I think that John put together an exceptional community there. I think it's safe to say I wouldn't have gone any distance with functional programming, and this meetup wouldn't exist if I hadn't attended LambdaConf, if I hadn't met all of the wonderful people that attended that conference. In fact, if you look at the list of past guests of this meetup, I would say a large proportion of them are former LambdaConf speakers. So I'm really glad that John was able to find time to join us. I know he's very popular and he speaks at a lot of meetups. I don't know how to describe him, a Haskell guy, a Scala guy. I think at one time maybe he was even a C++ guy. I think he is, he's just a seasoned technologist who at some point embraced functional programming and wanted to spread the word about it to as many people as possible. And he's done that in many ways, whether founding companies such as his latest company, Ziverge, founding his own conferences, founding the Fantasyland Institute, publishing books. I've even had the opportunity to help him with some of these things with LambdaConf in a few cases and with a few editorial projects. So it's exciting to be reacquainted once again and to have you speak to this group.
Thank you.
That is my pithy introduction. Now I'm going to hand things over to John. So once again, please hold your questions until the end. Feel free to type them into chat if you want. And you should be spotlit now. And
all right, thank you so much, Stephen, for that wonderful introduction. I don't apply to speak at talks anymore, but I do speak where my presence is welcomed, especially if a friend invites me to an event. I'm happy to do that. And it's a pleasure to be here tonight speaking to the Berlin Functional Programming Group. And it looks like even beyond, we have people attending from all over the world. So hello, everyone. Give me a moment here and I will share my screen. Let's see. All right, does this appear? Is this looking good?
Yes, looks
All
great.
Right. Fantastic. So hello, everyone, and welcome to my talk, Programming Without Type Classes. So in this talk, what I'm going to do is I'm going to share my experience, my real-world experience, trying to make functional programming more accessible to commercial developers. And before I do this in this talk, which is Programming Without Type Classes, I want to make the following point, and that is probably everyone in this meetup group is very passionate, like myself, about functional programming. We love FP. We love the way it changes our ability to reason about software and test it and to refactor it, the ability to know at compile time that our code is going to work as specified in production. So we're all FP fanboys and fangirls. We all love FP. And we all want to see FP win. I think almost everyone here probably wants to see FP get more recognition that we know that it deserves, get more percentage of the jobs out there, percentage of new projects, percentage of open source projects. We want to see functional programming win. And right now, FP is relatively niche. It's actually, I think, grown tremendously from 10 years ago. Today, you can get jobs doing full-time Haskell, full-time functional Scala, and lots of other FP positions, but it's still relatively small. And it can be so much more than that. I believe that functional programming can become, if not the dominant programming paradigm, then a significant entry to the market. It could be a significant competitor with OOP and procedural paradigms. Now, in order to get there from where we are today to FP becoming more mainstream, we have 2 different strategies available to us. Number one, we can teach some of the complex concepts that sometimes get people stumbling, tripping over themselves, struggling in the early days of learning and mastering functional programming. And that's where education is incredibly useful. And I've done a lot of stuff related to that myself. I've like Stephen said, I've organized conferences, I've given lots of talks, I've written lots of blog posts, and all of that material from myself and from many others is geared at helping to teach these more complex concepts, and not necessarily even more complex in all cases. Sometimes it's just more unfamiliar. We have this whole generation of programmers that knows what OOP is and knows what procedural coding is, that doesn't know what FP is. And so we've got to teach that, whether it's unfamiliar or complex. Education can be a valuable strategy to helping make sure functional programming wins. But then another strategy is to remove some of the complexity associated with functional programming. And you might say, well, that will make it not FP, but really, what is FP? Well, FP is programming with functions, and I personally think it's programming with values, with pure functions. That's the definition of FP that comes from Lambda calculus. And there are lots of things that we stack on top of that, not all of which we need. And sometimes we have different ways to formulate a given level or a given solution to a problem. And some of those ways require that you know more than other ways. So one of the strategies we can adopt if we want to make FP successful is we can remove the complexities, the stumbling blocks that get in people's way as they're especially getting started with functional programming. If you get started, if you taste the magic, if you discover how easy it is to reason about, test, and refactor your code, then a lot of those people will stick around longer and eventually learn the more complicated things. But it's so important, that top of the funnel is so important. So one of the things that I've tried to do, especially in recent years, is try to remove some of the complexity of learning FP for someone who is new to this. And I've done that in some of the open source software that I've worked on. I've done it in some of the more recent talks in which I try to stay away from a lot of the jargon. But it's important to recognize that no matter whether you're on the side of let's teach people category theory, let's teach people statically typed functional programming, let's help them master higher kind of types, let's help them become extremely powerful, well-informed developers that are capable of using all of these different abstractions and tools that statically typed FP brings to bear on business problems. Or whether you're more of the camp, let's try to remove the things that are not essential and focus on the more essential things so that we can, in so doing, open up, expand the top of that funnel, which will ensure that we have more people coming down the pipeline who can later master the more complicated, esoteric, or unfamiliar concepts inside functional programming, no matter whether you're of the first camp or the second camp, or even both. There's no saying you can't be a member of both camps. Honestly, our goal is 100% the same. We want functional programming to win. And so you're going to hear stuff from my perspective, which is more removing complexity. And that is not to say that it is competitive in any way with the attempt to teach people more complex concepts. They're complementary strategies, and I think it makes sense to pursue them both. We need people who are constantly evangelizing and teaching even more complicated concepts, as well as people who are continuously trying to find a way, like Elm, for example, to make FP simpler and more accessible to mainstream developers without a background. So in this talk, what I am going to emphasize is that type classes in particular, they provide a tremendous amount of value. But if our goal is to increase adoption in functional programming, then as library authors and as builders of code that other people consume, so this could be in a team, it can make sense to minimize the use of type classes, and instead of using type classes, to adopt a variety of alternatives. This doesn't necessarily mean that you can't have them, you can't use them, or so on and so forth. It only means that there are other strategies available to you as a builder, as a maker, as someone who knows FP and wants to make it successful. There are other tools that you have other than education. You have the ability to make things simpler and more accessible merely by changing your use of type classes, or in some cases, substituting the use of type classes for one of the alternatives that I'll talk about in this presentation today. So my agenda is to first introduce abstraction, because abstraction is intimately related to why type classes exist. Type classes exist because of abstraction. Then I'm going to tell you all the good, the bad, and the ugly about type classes, and there's a lot to love, and also there's a lot that maybe could be improved upon that I'll spend a few moments talking about so you can understand where I'm coming from. And then in section 3, really the highlight of this presentation, I'm going to give you some tools that you can use to free yourself from type classes. And these tools are ones that I and other contributors in the functional Scala ecosystem, the ZO side of things, have been working on for the past number of 3 years. We found a lot of different techniques that you can use to get the power of type classes without the usability problems that type classes sometimes have. And I'll explore those in section 3. And then finally, I'm going to give you a summary of the presentation and maybe point you in the direction of learning more, as well as take questions at the end. Abstraction. So if we want to build a data type that can store a list of integers, then we can do that in virtually any programming language by using what's so-called monomorphic data type. In a monomorphic data type like this int list here, we are building a list that can only contain integers. This is a linked list, a forward linked list that can only contain integers. And it works fine if our needs are limited to lists that only contain integers. But what happens when we come along and start need to storing strings in a list? In that case, we have to create another data type, which is designed for storing sequences of string values. And then that works well enough for that use case, but then we might actually need a list that is capable of storing sequences of Boolean values. So in order to do that, we have to invent another data type. And notice here that there's a lot of similarities on these different data types, actually. If you squint your eyes, you can sort of see they all have the same basic structure. What we're seeing in this monomorphic code is duplication. And how we solve that in programming languages with parametric polymorphism is we introduce type parameters for the data type. We parameterize the data type on a type parameter. And this is called generics over in the Java side of things and sometimes in Scala land, and it's called parametric polymorphism in the Haskell world. And what it allows us to do is see two different lists as having the same structure. So over on the left-hand side, we have a list of the smiling faces, and over on the right-hand side, we have a list of the smiling imps. And those look different, right? They look different. They're storing different things. But if we squint, there's a way to see those two different things as having similar structure, and that involves basically creating a placeholder, a little hole, a little template inside every element of the list. And now we can see both of those two different lists as having similar structure. The only difference is in one case, we substitute the smiling face into those boxes. And in the other case, we substitute the smiling imp into those boxes. And this leads me to a definition for abstraction that I quite like. So abstraction involves forgetting the ways that data types are different so we can see the ways in which they're similar. So there's lots of different data types out there, and they are different. They have different names, they have different structure, but sometimes it's convenient for us to be able to forget the ways they're different so that we can see or discover or remember the ways in which they're similar. And this can lead to a dramatic reduction in the amount of code duplication. We do that using parametric polymorphism or generics. As programmers everywhere are discovering, it's almost impossible, in my opinion, to introduce a new statically typed programming language without support for this feature, because otherwise, like the Go programmers are finding out, it just leads to too much duplication. All right, so parametric polymorphism, in particular data types that are generic, that have these type parameters, are how we create reusable data structures. Reusable data structures like lists that can work with elements of any type. Reusable data structures like maps that can work with keys and values of any types. Reusable either data types that can handle success and failure regardless of the particular details of how a given bit of code succeeds or fails. That's a key to reusability. Parametric polymorphism is the key to reusability. But it's not enough, honestly. Parametric polymorphism is not enough to complete abstraction, because parametric polymorphism allows us to see different data types as being similar by forgetting the element type or the key and value type and so forth, but it doesn't allow us to capture the ways that different things are the same. And let me give you an example of what are the implications of this. So if we had that monomorphic definition of a list of integers, then it's very easy for us to define a function that can sort that list of integers. So how can we sort this list of integers? Well, we just choose an algorithm like quicksort or partition sort, merge sort, whatever, and we compare the integers to see which one comes first, and then we just rearrange all of those elements in the list until it's totally ordered. That's something we don't even have to think about when we are working with monomorphic code. But when we switch over into the world of polymorphic code, so when we make our list types forget the elements, and so they become polymorphic on the element type, and now these lists can contain elements of any type A, then we have a problem with generic code. We're no longer able to write generic code. Take a look at these definitions of sort. These sort methods here, or functions, they try to sort a list of A's for any element type A, but they actually can't do it. There's no way to implement these functions. And that's because these functions, they don't have any information on the elements of type A. They have no way to see which A comes before which other A. And so that leads to the following dimension, which I encourage you to use when you're thinking about parametric polymorphism and abstraction. There is a dimension of abstraction, and on the one side is purely monomorphic data structures. These are data structures, data types, where you know all of the concrete details about what's inside them. For example, that list of integers is a monomorphic data type. It doesn't use polymorphism, and there's no generic type parameters in it. It's just a list of integers. And then on the flip side, you can go all the way to the other side, which is polymorphic. Well, actually, midway down probably is the polymorphic list. And in the polymorphic list, you don't know what the element type is because you're polymorphic in the element type. And then over even further to the right, you don't even know that you're working with the list. You actually just know that you're working with something that has kind star to star and maybe has list-like properties associated with it, like some type class or some interface in Java or whatever. So this dimension, monomorphism to polymorphism, actually maps directly to the following dimension, which is one of structure. It's a measure of structure. So on the left-hand side, you have all structure available to you. You have the full sense of what types you're working with and what capabilities those types possess. And on the right-hand side, you have no structure at all. You don't know anything. You have no details whatsoever. What that looks like in this case is structure is more or less a measure of the set of propositions that are known to be true about a data type. So that means if that inside that set of propositions we know to be true about a data type, there's tons of things in there, then we have a lot of structure. On the other hand, if there's almost nothing in there, then we have very little or maybe even no structure. So structure is a measure of how much we know to be true about a data type. And it maps directly to that polymorphism axis. In the case of integers, the structure of integers, these are the set of all propositions we know to be true of integers, and they include properties like a plus 0 is equal to a, or a times 0 is equal to 0, and so forth. And they include many, many other properties as well. So there's many statements, actually whole books have been written on the set of things that we know to be true about integers. This is just a small sampling. And of course, all these, a lot of them can be derived from the definition of an integer together with some sort of system for reasoning. But nonetheless, these are the set of all statements we know to be true about integers. So integers, there's a lot of rich structure, incredibly rich structure. Now, on the other hand, take a method or data type with a generic type parameter, the polymorphic type parameter. What do we know to be true about that? Well, actually, we don't know anything to be true about that. If you are provided with some value of type A and you don't know what that type is, then there's nothing that you can say that is true of that data type. Nothing at all. So you don't know anything. Actually, your structure is a point. It's a point. That set contains nothing. It's an empty. It's the empty set. That is the complete absence of structure. And so now you can see all of these superimposed on this diagram that I've drawn. You can see on the left-hand side, we have all the structure in the world. On the right-hand side, we have no structure. What polymorphism does is it allows us to go from having all structure to throwing structure away. So we throw structure away. As we add polymorphism, we throw more and more structure away until if we have something that's totally polymorphic, then on the right-hand side, we're way over on the right-hand side where we have no structure. We can't actually solve many classes of problems because we don't possess any details about what this concrete data type is or what sets of capabilities we have on that concrete data type. Now, while polymorphism throws structure away, type classes are a technique in functional programming that can be used to add structure into a problem to allow us to gain the set of capabilities necessary to solve that problem. So polymorphism throws structure away, type classes add structure. Now you might be thinking, well, why throw structure away with polymorphism if we're just going to add it with type classes? And that's a good question, but remember, in order to write generic code, we have to forget the ways in which data types are different so that we can remember the ways in which they're similar, which means we want to forget some details. So we need some polymorphism, but also we want to remember the ways in which they're similar. So we need type classes, or maybe we need subtype polymorphism. We need something in order to regain the structure that allows us to solve the class of problems that we're trying to solve on these generic data types. So we need them both. Without polymorphism, we can't see that different things are similar because all we know is their fine-grained structure. We can't write code that treats them as being similar. And without type classes, we have highly polymorphic code. We can't solve even basic problems like sorting a list of A's because we don't know which A comes before which A. So these two aspects are of critical importance to abstraction. You can't abstract without both of them, or at least something similar to them. Throwing away details, concrete details, and then regaining a notion of how different things are in fact similar to one another. So bringing this back to my discussion about structure, I hope you can see now that polymorphism discards structure. It throws it away. Functions that are polymorphic, data types that are polymorphic, they don't know about the structure of the types that they operate on. And then type classes allow us to write functions, generic methods, generic code, generic logic that recovers some structure necessary to solve the problem at hand, while still being general enough to work across many different data types that all possess that structure. We solve that in the case of this sorting method by using a type class called ord. And this type class allows us to, it gives us basically the minimum set of capabilities we need in order to perform a sort. And that is to answer the question, if we have two values of type A, which one comes before which other one? If we have that, then finally we can solve the generic sort. And now we can have our cake and eat it too. This generic code can work across all lists. It doesn't care what the element type is, provided you can give it the bare minimum amount of structure necessary to solve the problem, which is determining the order in which two elements occur in a sequence. There are two elements to every type class. I'm not teaching type classes in here, but I want to review them because I know some of you are less familiar with them, especially if you're coming from Scala, which doesn't have first class support for type classes. Sort of it does in Scala 3, but not really in Scala 2. So there's two components to type classes. One is the type class definition. And the type class definition defines the structure that we can recover by using this type class. What the type class definition is it's a set of constructors and or operators that operate on values of a given type. They give us a set of capabilities on a type. So ord A gives us a set of capabilities on that type A. It gives us the ability to see which A comes first in a sequence. But type classes, no matter what they are, they always only give us a set of capabilities on a given type. That's the definition of the type class. And then, of course, we create what are called type class instances, which can be regarded as proofs or as providing an implementation of this definition for a given concrete data type. So in this case, we might want to define, basically tell the compiler how to order two ints, and we do that by supplying an instance of ord that implements the compare function in a way that's sensible and accords with the definition of that ord type class. So the type class definitions, they provide what set of capabilities we're interested in talking about with respect to this type class. And then the type class instances, they actually provide concrete implementation of this type class for a given data type. Basically, they're supplying that set of capabilities for a given fixed data type. They're both important. It's important to be able to talk about the type class as well as to be able to supply implementations of this type class for given concrete data types that do in fact possess that degree of structure. And if a given data type cannot be compared for ordering, for example, then you would simply not supply an instance for that type. For example, functions cannot be compared. We can't tell which function comes before which function. That doesn't even make sense. So we would not supply an instance of ord for a function type, but we would supply it for an int type and for a string type and for many other types. Not all types can be viewed as being the same, right? Type classes abstraction lets us see the similarities between types, but sometimes types are not similar. There's not a whole lot in common between an int and a function type. Those are different things. We can't use them in the same way. Generic code that works with one is not going to, in general, work with the other. So type class definitions allow us to define structure, and type class instances allow us to recover that structure for a given type. Now, this is all well and good, right? It allows us to solve the generic sort problem and a huge variety of other problems. Basically, type class driven programming is incredibly powerful, and it allows you to compactly and concisely solve a whole host of problems that you encounter when you're trying to do statically typed functional programming. But there are drawbacks. These drawbacks are not fatal. They haven't stopped, I would say, probably tens of thousands, maybe even more, developers from learning them and becoming very proficient and productive at type class driven development. But it's fair to acknowledge those drawbacks and to see that there are trade-offs. Life is not black and white. There's good and bad in everything. And there's many pros of type classes. I love type classes myself, but there are also some drawbacks. So let me point out some of the drawbacks that come when we go all in on the type class approach. And one of them is the anti-modularity of type classes. So type classes can actually be viewed as global, piecewise defined functions that map from a given type to a type class instance on that type. So it's like we have the compiler supplies us with a very magical function called lookup, and we give it a type. For example, we give it the type int, and we get back the ord instance for int. So we get back a way to compare two ints to see which one comes first. So the fact that this is a global and piecewise defined and magical supplied by the compiler makes type classes very anti-modular, basically. So the compiler needs awareness of all sets of type class instances that are defined for these data types across the whole code base, across everything. So it means that it has rather severe implications for separate compilation units and also for modularity. Down here in this part of your code, it would be nice if you could sort of use your own definition of what ordering for ints is. And then up here, it would be nice if it could have its own definition. And it could be nice if you could sort of nest these things in a nice, elegant way. And that's not really a fit for type classes. Type classes are, and they want to be, this global that is defined with respect to the entire universe of code, not just a given separate compilation unit. They want to be this globally defined, piecewise defined function from type to type class instance. And that just leads to inherent difficulties. And there are workarounds for all the anti-modularity associated with type class have workarounds, but they get nasty. For example, new typing is one way that we regain modularity with type classes, and we introduce a type wrapper that allows us to select for a different type class instance in this given case. But that's a problem as well, because it leads to sort of an exponential problem in creating type class wrappers and delegating and so forth. And plus it's lots of boilerplate and it's just nasty. And all of this comes from the fact that type classes are anti-modular. They want that global view into everything, but sometimes locally we want a specific definition for ordering for integers or for ordering for strings or whatever type class we're using. And honestly, type classes don't have a really great satisfying solution to that problem. They do have a solution to that problem, as with all things, but it feels boilerplatey, it feels clunky, it's not very pleasant to work with, it's very hard to explain. People see that and they push back against it. They don't want to have to do that. And that all stems from the anti-modularity associated with type classes, which is also why type classes are so amazing to use. That's interesting, is that the anti-modular aspect of type classes is why it's so beautiful and elegant and simple to use type classes in common cases. So there's a trade-off there. There's good and bad and everything. Another drawback that people don't often consider with type classes is that they are not first class, or at least type class instances are not first class values. Not in Haskell anyway, and they sort of are in Scala, but it's not easy to deal with them as such. Basically, the type class machinery in Haskell and Scala exists at a different level. It's not value-based machinery. And what I mean by that is it's not trivial to write, and we can't write a function that takes an instance of one type class and returns another instance of the same type class for a different type. Basically, we can't write operators that transform and combine type class instances. And that leads to all sorts of pain in the code that we work with. For example, I'll give you a great example of quick check. So quick check defines this type class called arbitrary A. And arbitrary A just says I can summon a gen of A for some type A. And the reason why it has this weird design, and by the way, gen of A is just an ordinary data type. Gen of A is just a data type that can generate A's for use in property-based testing frameworks. The reason why there's this weird design with the type class that can basically summon you gen of A for a given type, and then the data type gen of A, which can generate the A values, has to do with the fact that it is extraordinarily useful to be able to define operators on gen. We can't define operators, binary and unary operators on arbitrary. We can't transform arbitrary A's. We can't compose them together. But we can do that for gens because gens are ordinary values. Type classes introduce additional machinery that is above the level, the value-based expression-oriented machinery that we use to solve the majority of our problems. And so if you want to write instance transformers or instance combiners, you have to do them in a different language. It's a different sub-language of Scala or Haskell you use to solve those problems. You use the implicit machinery, given machinery in Scala 3. You use instances and dependencies and so forth in Haskell. You can solve a set of these problems. It's cumbersome. It's not easy to work with. You can't do that programmatically. All of that logic has to be done at compile time, so you can't do it on the fly. So the difference is here that because type classes introduce second class languages that are not value-based, expression-based, that your expressive power is limited whenever you choose to use type classes, and also the ways in which you solve problems is going to be different. You need to buy into that sub-language, the sort of implicit or the instance-driven language. You need to use that alternate language in order to combine things and transform them. And you don't have any of that problem if you're just using ordinary values. That's why all of the Scala check or quick check successors like Hedgehog and whatnot, they said, look, this is not making sense here. We actually need to delete the arbitrary type class. And they did. They blew it away. And now you can use ordinary gen values, and it's a little bit more verbose, but it's extraordinarily powerful because it's trivial to define binary and unary operators and custom constructors for gen. And these things cannot be defined at the level of the type class machinery. It's just not possible. And then finally, and this is a rather large category, so I saved the best for last, type classes are associated with less than ideal ergonomics from the point of view of introducing someone who is new to all of this. So someone who's straight out of like a Java job or Python job, you plop them down in front of this type class machinery, and there's a lot of less than perfect ergonomics. The developer experience is not ideal. And let me give you a few different examples. So let's say you are plopped into a generic code base and you have all these type class definitions and all this parametric polymorphism, and you want to know which type class function you need in order to solve a given problem. Well, how do you know which function you need to solve a given problem? In this case, we might need bind, which comes from monad, which is a type class in category theoretic, statically typed functional programming. We might need that, but how do we know that we need it? So there's a discoverability problem associated with type classes. We need to know what the type classes are, what sets of capabilities these type classes provide, and what those capabilities mean for the concrete data types that we're working on. So if we're working on a tree, for example, then we need to know what monad, not only what monad is, but what sets of capabilities it provides and what those capabilities mean in the context of our tree in order to be able to know to call the bind function in this case for our to solve a given problem that we have. That's tough. That is tough. And that's probably from my experience teaching functional programming, that's possibly the number one problem that people have with type classes is not seeing what it gives you, not seeing in which circumstances you need what, not even knowing which type classes exist. It's a big discoverability problem. And obviously the educational approach to solving this problem is to teach people all the common type classes, all the common operations, and to give them a good sense of how to use these different operations to solve given problems. And that can work and does work, but there are other ways as well, as I hope to show you later over the course of this presentation. Another problem is that we have a situation where type classes are domain agnostic. And that means type classes, both the name of the type class, as well as all the set of operations and capabilities it provides, it doesn't care what the domain is. And that's because, remember, type classes are used for abstraction. And in abstraction, we want to be able to write generic code. And this generic code will work against many different data types, and it will do many different things depending on the concrete details of those data types. And that means that there's a tendency to make these type classes super ultra domain agnostic. They don't care the domain. The names have nothing to do with the domain, and the organization has nothing to do with the domain. Nothing is domain related at all. It is all domain agnostic. And on the other hand, there's another way of writing code that's more familiar to many developers, and that's domain specific. So in domain specific ways of writing code, the operators, the functions, the methods, the data types are all very specific, tailor purpose to that domain. And as a result, it can be maybe more obvious what these things do and what problems they solve and where they're located. It can cut down on many of the drawbacks associated with type class programming. An example of this is the semi-group append operator. So the semi-group append operator, it doesn't care what it's doing, and it does many different things. For example, in logical programming, it will explore different possibilities. It'll explore this set of possibilities as well as this set of possibilities in an effort to find a solution. In the case of IO type effects, it will perform this effect, but if that one fails, it will fall back and do this other effect. In the case of parser combinators, it's backtracking. It is try to parse this, and if that doesn't work out, then go over here and parse this other thing. Basically, it's prioritized alternation. So this single operator can mean lots of different things in different contexts, and that's not necessarily a good thing from the point of view of someone who is new to FP, because they want something that is tailored to their specific problem in their specific domain, they don't know to look for something that's generic. They're not really looking for a solution to a generic problem. They're looking for a solution to a specific problem with concrete data types. And that just hinders discoverability. One of the things that I can tell you from having been an entrepreneur and founded a few companies and built a few products is that I learned from marketing that people always go for the solution that is custom tailored to the problem that they have. In other words, they don't look for a platform, because a platform is a tool for building a solution. Rather, they look for a specific solution. If you are in the market for an e-commerce platform, or rather, if you want to sell your knitted hats to a global audience, then you actually don't look for an e-commerce platform. You look for a platform that helps you sell knitted hats to a global audience. And if there is such a thing, then that's the one you always choose. People have specific problems, and they look for specific solutions to those specific problems. That applies even in the world of development. And it means that there's a massive discoverability issue associated with these domain agnostic names. In addition, there's the whole set of usability problems that come from our attempt to use type classes. So let's say we try to call some generic function like foldMap on a tree. Then we're going to get back, and not just foldMap, by the way, but basically any generic code in any of these functional programming libraries. If you try to call it on your own data structure, you might be presented with an error message that looks something like this. It says, error, monoid instance not found for person. Okay, so if you've been functional programming for a while, you know what that means. I know what that means. It's like, no big deal, whatever. I'm gonna derive an instance of monoid for my person data type, or discover that that's not a sensible thing to do because my person data type does not possess monoidal structure, which could happen in the process of me trying to write that. But that's learned. That's learned. The simplicity is learned. So this is no longer confusing to most of us. We look at this and we're like, whatever, but no big deal. But you have to view this from the perspective of someone who has never before written a single line of polymorphic code or type class based code. They've never written any of this. And they encounter an error message like this, and they are totally confused, utterly and totally confused. And so they never come down the funnel. The top of our funnel is so narrow, people aren't getting down there lower level where they would invest in discovering what this means. They're turned away at the door, basically, because of the high usability costs associated with this code that we don't even see. We don't even see, monoid, whatever, semi-group, functor, applicative, whatever. It's all simple to us because we've been doing it for so long, but it's not simple. It's unfamiliar. It is extremely unfamiliar. And so someone might look at an error message like this, and they might say, what the heck is a monoid? And also, this is irrational. I will grant that. But the fact that it's called monoid can be scary for people. Monoid sounds like some crazy thing in math, and everyone hates math. Everyone hates math because their teachers program them to hate math, more or less, by trying to use human brains as calculators and many other, unfortunate mistakes of elementary and middle school and high school education. People are that way. They hate math. And that sounds very mathy. It sounds scary. And not only that, but there's no simple fix to understanding what a monoid is. You have to be willing to invest in yourself, which is good for you. It is absolutely good for you. You should do it, but you have to be willing to take those steps to invest to discover what algebraic structure is, what a monoid is, what a semigroup is, magma, all the other abstractions from sort of abstract algebra. They're all incredibly useful, but understanding them is non-trivial. Seeing this is scary. And yeah, it's a monoid is just a magma that's associative with an identity under composition, right? We all know that. But it's not so simple. It's not so obvious. And it scares people away. It pushes people away at the door, unfortunately. And then the next thing they run into is, what the heck is an instance, right? What is an instance? Well, it's just an instance of a type class for a given type, right? We know that. But explaining that is not so simple. Explaining what a type class instance is and how it relates to a type class definition what is a type class? We have to explain the concept of a type class as being a set of operations and constructors on values of some type that explains algebraic laws, and explain resolution mechanisms, and explain all of these different unrelated things, everything from math to programming language semantics. We have to explain all of that in order for them to truly get the solution to fixing this error message. Fundamentally, what they want to do is they just want to make this error message go away and do whatever it is they want to do. That assumes they discovered flatMap. In reality, because of the discoverability issue that I mentioned, they probably would never discover flatMap. But if they did, or someone told them to use some generic bit of functionality, they read that in a documentation, they copied it from Stack Overflow, they saw it on a microsite somewhere, then they would run into this set of problems, which further prevents them from making progress. So all of these drawbacks are significant. You look at them, yes, you can solve them with education, but this is a lot of education. And those of you who have been doing this for a long time, I think, don't appreciate how much education goes in to achieving the level of mastery that you have. I'm not saying that this is rocket science. I'm not saying that you couldn't teach it to as 8-year-old. You could easily teach this to an 8-year-old given sufficient time and motivation on both people's parts, but it is work, and it's work that you're asking people to do before necessarily they've had a reason to do that. So how do we solve these problems? Well, I'm not going to tell you how to solve them. I'm not even necessarily going to tell you that they're definite problems. If you're working with a team of people who already know these data types and you can hire more people like that, then fine, more power to you, stick with that. On the other hand, if you're in the position of being a builder or a maker, and maybe you've tried the evangelism thing and it's not working, or maybe you want to keep trying that, but also you want new strategies, new tools available to you, then I'm going to give you a set of tools in this section that have worked well in the Zio ecosystem in trying to bring functional programming more into the mainstream. So these tools will help you remove more complex elements, remove the need for teaching, minimize the need for teaching in an effort to help more people jump on board the bandwagon of functional programming. And to some extent, they're complementary. Once you get people doing FP, of course, they can learn about other things, more esoteric things. But first, step one is just getting them on board with writing code in a functional style. And these techniques will, I hope, I think they've shown to do that to some degree in the Zio ecosystem. So tip number one, I recommend that you specialize as well as localize names of operators and constructors. What does that mean? Well, there's a continuum here, like I mentioned earlier, between things being domain specific on the one hand and domain agnostic on the other hand. And type classes, they're all on the domain agnostic side of the fence. Everything over there, it doesn't have descriptive names because it can't have descriptive names because it works across all domains. And then there's the very domain specific names which are rigidly fixed to concrete data types over on the other side of the fence. And what I would encourage you to do is stay away from domain agnostic names, or maybe have them there if you want, but at the very least, specialize the names, make them domain specific. And that means that maybe we would not necessarily use semi-group append to combine two different parsers, because how would you know to think that semi-group append actually combines two parsers in a fallback fashion? You would have to know quite a lot, and you would have that discoverability problem. So rather, just give that a name, give that a specific name, even if ultimately you're going to implement that by delegating to a type class instance. Give that operator a name that is specific to that domain. Don't be afraid of that. And of course, Haskell has plenty of great examples where this is done. Like we can concat lists, right? We can concat lists, which is great because people want to concat lists. People don't want to semi-group append lists. They want to concatenate two lists together. And they want to see that documentation that says, oh, this is the function that allows you to concatenate two lists. Well, we like that, but also, of course, we have the semi-group append if you want to do it that way. Give your operators and your constructors names that are specific to those concrete data types, even if you also provide instances of common type classes for those data types. Put the documentation there and put everything there, make that language of the documentation concrete and tangible so that people know it solves the exact specific concrete pain that they have. In addition, you can localize names. So not only make them very specific, domain specific, but you can localize them. What do I mean by that? Well, basically, this is a technique that you can use to improve discoverability. You can place operators together with the data types that they're defined on. So if the only way I have of combining two parsers, for example, is by importing a data semigroup operator so that I can then, append two parsers together, then I have a discoverability problem because I have to know to import that specific package and get that operator and so forth. And that relies on me because it's something that I have to have been trained about. Maybe I can read it somewhere in a comment on a microsite or whatever, but there's a discoverability problem. And localizing the name means to take all of those domain-specific operators that you create, even if they're backed by the type class instances, you create them yourself. They're domain-specific, they're specialized. You place them together with the data types. And this is an area in which object-oriented programming languages actually excel. They have extraordinarily powerful tools of code organization, so we can then do better than just merely putting them in the same package as the data type. In the world of Scala, we can actually put them on that data type as methods because OOP gives us the ability to have functions that operate on the data. So we can organize them there where we know for a fact all the Java and Scala programmers are going to find them because their IDEs tell them every single method that is on that data type. So we move from a discoverability problem to almost entirely eliminating that problem merely by localizing these domain-specific operator names in the packages or the data types where they're defined. That is a tremendous principle for organizing information that allows us to open up gateways to self-service discoverability. They don't necessarily need documentation anymore because everyone knows if you want functionality related to a data type, you look in the same place where the data type is defined. This is an example in Zio where both techniques are combined to great effect. So in this case, if you want to iterate over a bunch of requests, for example, and you want to perform some effect for every single request, and you want to collect back all of those results together for subsequent processing, then you use the Zio for each operator. That for each operator is defined in the companion object of the Zio data type, which is the same place that all the other constructors for Zio data types are defined. So if you want to know how to build a Zio, just look inside the companion object for the Zio data type, and you'll find all the different ways you have of building Zio effects. And Java programmers know that. Scala programmers know that. They know where to look to find that. So it's very good code organization. It's localization. All of that functionality is there. Even if you could access some of that functionality through type classes, it is also there in the companion object together with the data type that it provides capabilities on. In addition, the very generic operator traverse from the foldable type class has been specialized. It's called for each here. Why is it called for each? Well, it's called for each because many times when developers new to functional programming are looking for a way to do a for loop on a bunch of values and perform effects for every value, they're looking for something like for each. They're in that for each mindset. They're thinking, I need a for loop. I need Zio's version of a for loop. And so they find that for each, and then they write it and they use it without issue. And then developers who are new to the code, so their people are being hired to the team, they look at that for each and they're like, I have some idea of what this does. I don't know maybe exactly what it does or why it's done this way, but I sort of know the intent of this code. And that's because that operator name has been chosen specifically for the domain of input-output. So Zio is an IO type for you Haskell programmers, and that for each name has been chosen specifically for that IO type. For each is not a good name for traverse in general because traverse is just too general for that, right? Traverse does many different things. It doesn't necessarily recreate the for loop from Java, but in the domain of IO, Zio being the sort of most powerful effect type in which you model all your side effects in your application, that makes a ton of sense. It's maybe not the best possible name, but it's certainly, it's connecting with new developers a lot more than the Traverse name. Another technique that you can use to eliminate type classes, so the first sets of techniques are not necessarily eliminating because you can live in harmony with type classes, but nonetheless, they are alongside type classes at the very least, and maybe eliminating type classes. So a lot of programmers, I think functional programmers, fell into this mindset that we would create these data types with rich algebraic structure, and we would expose the algebraic structure through type classes. Wrong idea, bad idea. I mean, do that if you want, of course, but also expose that rich structure through domain-specific names that are co-located with the data types. Okay, that's that first section. Do that. That's what Zio does. It's been enormously effective in helping people get it because it solves the discoverability issues. Now, what happens though if you want to eliminate type classes from parts of a code base? How can you do that? Well, one technique is to inline the type class. And I'll show you what this means, but let's look at this code snippet here. So here we have some generic code that says for all types A that provide an instance of the show type class for A, I can take a tree of A and render that to a string. This should make sense to you. In order to render a tree of A to a string, we need to know how to render the A to a string, basically. That's what this code is saying. It should make sense. So this is perfectly reasonable generic code. But a developer using this has all the drawbacks that I mentioned. They go to call render tree. First off, this code is specialized, actually. It's specialized because it says render tree. So it's already satisfying the first characteristic. And if it's located in the tree package or on the tree data type, then it's already satisfying specialized and localized names. So it's already part of the way there. This could, of course, just be a show instance on tree, but then people would have to know about the show type class. So this code is halfway there, but still, if you call render tree on your own data type, so you call it on a tree of person values, then you get back that same error message, and then now you have to understand everything. You start pulling that thread, and it ends up, yes, with you becoming a master of functional programming or some such, but long before then you may abandon the attempt because there's just so much background involved. So how could we eliminate this? Well, one simple technique is just to inline the type class. So here, what we want to do is convert every A into a string. So what we can require the user do before they call render tree is to pre-convert those A's into strings. In other words, we change the signature of render tree to accept a tree of string and to convert that to a string. And now they call render tree and they get some error message saying that their A is not a string. They know how to fix that. Or at least they have an idea of how to fix that. They know they need to turn those A's into a string somehow. And of course, that can be reflected in the documentation of render tree. It can say, you know, if you want to render an arbitrary tree, you better convert your A's into strings. This is an example, a very simple example of requiring what you need. Don't require a type class, rather just require the raw sets of capabilities that you need that type class for. And in a simple example, it's as trivial as this. There's an example in ZioTest that uses this exact technique where instead of requiring a show for A, we simply require that you provide a string representation for that A at that same point up front in advance. And that totally deletes the need for a type class there. You can also use this in more complicated examples. So here we have a combined tree operation, which is capable of combining two generic trees of A's into a single tree of A. And this might have very complicated logic to combine these two trees, but at the end of the day, in the event of collisions, what it's got to do is it has two A's and it needs to combine these two A's into one. This solution here, this generic code requires type classes. So one way we can improve the usability of this is to eliminate the type class by inlining it. So in this case, all we really need is a way to combine two A's into one. So we can reflect that in the type signature in the method name here, and we can say combine tree with the specified function. So this is fold left, basically. It's fold left and fold right. All of these are are the sort of inline versions of fold map. So you don't need to use fold map because we have fold left and fold right. And probably, if you're not working with an extremely advanced team, you already know that developers are way more comfortable reaching for fold left or fold right than they are fold map. And that's because fold left and fold right simply states in its signature, you need to be able to combine those two A's. So if you happen to know what semigroups are and you have a semigroup instance for your type, you can easily pass that definition of append or combine into the combine tree with, but the reverse is not true. If you're calling combine tree and it requires the semigroup, how are you going to solve the problem? You have your data type. That data type does not have a semigroup instance. How are you going to call that function? That's a rabbit trail that will take you a very long time to pursue. So just inline the type class, require what it needs. And then the final technique that is by far the most powerful, this is extraordinarily powerful, and lets you eliminate many other uses of type classes in a way that, in my opinion, dramatically improves ergonomics and usability, is to use free structures. Free structures are very, very powerful. And they do have drawbacks. There is no panacea. Every solution, every way of introducing type classes that you could possibly think of will have its own set of drawbacks that have to be measured carefully. It's my opinion, though, that if you're optimizing specifically for the top of that funnel, if you're optimizing for developer experience, ergonomics, specifically with respect to people new to functional programming, then going all in on free structures makes a lot of sense, because yes, there are drawbacks, but those drawbacks are necessary if you want to optimize for that goal. So take a look at this code here, which is requiring a type class on A here. It says it's going to require a monoid on A so that it can batch up all these individual queries and then submit them to some sort of batch processing that can more efficiently execute them all, maybe in parallel, who knows. And then at the end of the day, we're going to get back an IOA. Why does this code require a monoid A? Well, first off, the list might be empty. If the list is empty, then we need some way to produce an A. So we need the monoid. Also, if that list contains more than one query, then we need a way to combine those A's into a single A. So this code, this generic code, is perfectly reasonable in requiring a type class for A. But also it has all those usability drawbacks. How do we solve this problem? Well, we introduce a free monoid on A. So this is the general technique. Instead of requiring a type class X, build your own free structure for X and return that instead. I'll talk about why here in a second as I flesh out this example. But possibly you already know, if you know about monoids, you probably already know that list is the free monoid. So list is a free monoid. For any type A, list of A is a monoid for A. It requires no structure on the A. And that's because you have the empty list for your monoidal identity element, and then you have list concatenation for the append or combine of the semigroup operation. So we can refactor this query here to simply return a list of A's. And then push, if the user wants to combine those A's into one, require them to do that on a concrete list, because the user knows how to work with a list. They know how to fold left or reduce, or if they're an FP programmer, they know how to fold map. They know how to do that with a list. We don't have to require, this generic code does not need to require that type class. It can merely use a free structure instead. Let's take a look, though, at a more complicated example. So let's say we have this operation called parallel that can take two IOs, and here I'm assuming IO has typed failures, which doesn't work out all that well in Haskell, but it works out pretty well in Scala, because in Scala we have subtyping, and in Scala 3 union types and so forth. So type failures make a lot more sense, and they're a lot higher ergonomics in Scala than they are in Haskell. So let's assume we're working with some IO type with typed failures, and we want an operation that can basically do two things in parallel. Now, if we do two things in parallel, then we have a bit of a problem, because here are the following possible outcomes that come from doing two things in parallel. Either the left-hand side fails, or the right-hand side fails, or both fail. In addition, we have another problem, and that other problem is basically that we may be in a situation where either the left or the right-hand side or both have some finalization logic. So basically try finally. So they have some finalization logic. It's possible the finalization logic itself could fail. And as a result, so when we call parallel on two different IOs, then we can actually generate both sequential errors, and a sequential error happens when one side or the other fails in a primary reason, and then also the finalization logic fails as well. So we get, and that can be nested, so we can get any number of sequential errors from either the left-hand side or the right-hand side. Or we can have parallel errors, and the parallel errors arise from the fact that we're running both of these things in parallel, so they can both fail. And furthermore, that can be nested as well. So the left-hand side might itself be the composition of two other effects in parallel, and so forth. So there's no restriction on the nature of this tree. Basically, you should be picturing a tree with parallel and sequential nodes. There's no restriction on the nature of that tree. Now, if you know something about abstract algebra, and you recognize sort of a sane way to view error equality, distribution basically of parallel errors over sequential errors, then you can see here that in order for us to do this composition, we need semi-ring capabilities on the user-defined error type E. That's the exact set of, actually there's multiple definitions of semi-ring, but you can define a semi-ring in such a fashion that semi-ring capabilities are what you need here in order to do lossless error composition on the user-defined error type in E, because that gives you the ability to generate sequential errors and compose them all together, as well as generate parallel errors and compose all those together. So this code here, it requires semi-ring E. It requires that type class. It has all of the drawbacks associated with requiring a type class. And then it has an additional one. So all of you were probably familiar with the monoid. You may not be familiar with a semi-ring. What are you going to do if your error type E is not a semi-ring? If it does not have the structure of a semi-ring? Well, you can always use a new type, some lossy type that satisfies the laws. That's what's done for monoid. The last and first monoids are lossy monoids. They're used in cases where, no, we don't really have a monoid. We want to throw away one side or the other because we don't have a way to combine them. So new types are how you select these instances for data types that maybe don't necessarily have that intrinsic property. So if you have your own error type E and it doesn't have the structure of a semi-ring, you have a big usability problem, because now you've got to lift your error types up to something else that does have that structure. And then once you call parallel, you can now sort of downgrade it to something without that structure. So that is unpleasant. That is very unpleasant. It's a big usability issue. So in addition to all the drawbacks that I mentioned before, if your data type does not have the structure required by a definition like this, which it needs to have, then you're screwed. There's no easy fix. The fixes that exist are very painful. It's not very pleasant to use code like that. So what's the solution? Well, the solution is to build a free structure that possesses all of the capabilities required or provided by that type class. In this case, we need sequential parallel composition, the ability to fail, and maybe we need some sort of identity for the semi-ring. It depends on your use case, but we need some sort of some type, some ADT like this, which introduces a free structure that allows us to achieve parallel and sequential combination of errors. And then once we do this, we can actually subsume it in the main data type. So we can have an operator on IO that lets you peek into that E and lift it up to be a full cause of E. And we can have another operator that, given a cause of E, will let you subsume that. So you don't have to see that free structure unless you want. And this is the solution that Zio does, by the way. So Zio actually has built into it a free structure called cause, which is a free semi-ring. which is the basis of all error composition. And it doesn't complicate the API at all because that's hidden beneath a type parameter. And there exist dual operations allowing you to reveal the presence of that cause as well as sort of subsume the existence of that cause so you don't have to think about it anymore. So when you want to deal with the structure of that semi-ring, you can, but you don't have to. And also, you never need to know what a semi-ring. I would venture to say that 99.99% of Zio users have no idea what a semi-ring is. But if they happen to see a cause in their code, they drill down and they can see it looks something like this, and then they can understand that. They're like, oh, sequential errors here, and parallel errors here, and singleton errors here. They can understand that. Why? Because every single name here is domain specific and it's all localized. All of the methods, operators, and functions on a cause are right there, and they all have domain specific names. These are not called plus and times, and they would be called that. If you had a free structure in an FP library, then this would be called free semi-ring. And you would be violating my first recommendation, which is to specialize in localized names. You would just have generic plus and times and identity and some other singleton for leaf unit, probably it would be called, or worse, a pure point, and then you would call this ADT free semi-ring, all of which would be incredibly confusing. But this data type here, as it exists in Zio, it has a domain-specific name. Cause of E is the full cause behind why you got a failure of type E, and you have sequential and parallel ways to fail, as well as a sort of root failure cause, which is just called fail. And then I'll give you another example of this technique, which is extraordinarily powerful. This technique, by the way, not only did it delete the need for a type class here, but it means that code becomes tremendously more ergonomic, because when your own data type does not possess that structure, then the structure of these operations is still captured in the underlying free structure, but you can call the methods like you want, sort of willy-nilly, like you want, whenever you want, on any data type. You don't have to provide any instance of this type class for your data type. So in cases where it doesn't make sense, like actually it's common in the world of Java to use throwable or exception as an error type. And those things are not free semi-rings, for sure not. And actually there's no way to make them free semi-rings. Sorry, yes, there's no way to make them semi-rings. They're not semi-rings, and you can't make them semi-rings. So it would be very inconvenient. Whereas this, you can use it with anything. You can use it with string error messages or whatever. The usability is extraordinarily high from this technique. And honestly, the usability is so high that even if I were building Zio for an audience that knew exactly what all these type classes were and how to use them, how to make type class instances, I still wouldn't go back. I would not change this decision. The usability of this approach is simply too high to ignore, in my opinion. Here's another example that you've probably actually felt the pain of. A lot of FP libraries have this validation data type, and this validation data type is in your face about requiring either a semi-group or sometimes a monoid for the error type. So validation EA will either fail with an error or it will succeed with a value of type A. And all the operations, the generic operations that are exposed for validation, first off, many of them are provided via instances, so they have generic domain agnostic names. But even if you clean that up and do it right, so even if you specialize and localize the names, you're left with a lot of methods that require a way to combine errors of type E. And that's because when you're doing validation, when you're doing this validation and this validation, it's possible both of them fail. In fact, that's the main use case for the validation data type over the other data type, is the fact that it's going to combine the errors into one. But you have all the usability problems associated with requiring this semi-group E or monoid E everywhere. And in fact, these usability problems are so severe, even in the statically typed category theoretic branch of functional programming, that people invent type aliases like validation NEL and lots of little helper functions to help work around these usability problems. Now, how could we solve this problem in a way that maximizes usability? Well, we rip out the type class. We rip it out first by introducing a free structure, which is capable of combining errors. So this non-empty A we could actually give this probably a better name, validation failure or something. And we would say that either validation failure is one failure or it's both failures. So this is a generic free structure. I would encourage you to, if you were doing this for real, specialize this. Don't necessarily make it generic. Make it so that when people see this, they know what it is from its name and from all the methods, domain specific, that are available on it. Introduce that free structure and then use it as part of the definition of a validation. So now when you run a validation, you get either the non-empty error or the success value. So you actually get the free structure back. And as a result, all those compositions of errors have been accumulated into a list-like data structure. And now you as the user, when you run that validation and it fails, you get back all your errors. And it's at that point when you can decide what to do with them. Do you want to combine them because you know what semigroups are and because there is a semigroup defined for E? Okay, well, you can do that. If you don't want to combine them, because that's not sensible, you just want to print them out or transform them to something that is printing out all of the errors or whatever, you can do that as well, because you know how to work with the list. It doesn't matter what kind of programmer you are, you know how to work with a list and how to combine, transform, and traverse over all the elements of a list. So what this technique does is it basically defers things even further into the future. Why require type class instance? No, return a free structure. And returning that free structure allows the user to decide what to do. Are they going to back that? Are they going to translate that free structure into the underlying operations that it models through a type class instance? That's always a possibility. Or are they going to directly consume it using lower level, maybe non-polymorphic, non-type class based code that an advanced programmer would look at and would say, hey, there are better ways of doing that. It doesn't matter that there are better ways of doing that. The fact that we got the person to that point at all is all that matters. The fact that you are looking at a programmer who is engaging in what you might consider to be anti-patterns, looping over lists and traversing, fold lefting over lists just to aggregate errors and other sorts of things. That is what's called a really good problem to have. You got them past the hump, you got them down the funnel, and you can teach them more stuff over time. But step one is just making sure that they were pushed out the door. They made some progress down the path to becoming a purely functional program. So in general, these free structures, in my opinion, have the following benefits. Number one, they allow you to use specialized names. So the names of the free structures and their constructors, as well as all methods and functions that operate on them and that construct them, can all be chosen to be extremely domain specific. That will involve duplication. That's okay. It is okay, in my opinion, if your goal is optimizing developer ergonomics, to trade off duplication for accessibility and discoverability. So you specialize the names of everything like crazy. You also localize the names of all of the functions and the methods that construct and operate on these data types. Also, you don't encounter any error messages. So for example, when you combine two effects in parallel in Zio, you will never get any error messages. Ever. It's not even possible. You eliminate that possibility. There are no type classes. You've deleted all the type classes. So not only do people not have to create type class instances or understand what instances are or what type classes are, they don't have to even know that type classes exist inside the host language. And same way for type class instances. So you don't have any type class instances, which implies that you don't need to explain that concept. You won't have any orphan instances. You won't have any modularity problems. All of these problems just go away. All of your code is modular. All of these things that you're returning, free structures in general, are first class values. You can define operators for transforming and combining them, translating them from one structure to another, and so forth. That's the sales pitch. Obviously, I'm not going to talk about it in this talk, but there are drawbacks of approaching this style of development without using type classes. I'll be honest with you, there are some drawbacks, but also these benefits are, in my opinion, so incredibly compelling that if your number one goal is to get more people doing commercial functional programming, it makes sense to at least pay attention to some of these tools and to consider using them judiciously in your own code bases, in the libraries that you develop, in the pieces of your code that are going to be used by other developers, especially those developers who are new to the team, who are going to be coming in without a background in functional programming. So to recap what I've presented so far, abstraction is how we forget the way that different data types are different and remember the ways that they're similar. And we do the forgetting by parametric polymorphism, and we do the remembering by type classes. They allow us to throw away structure, but then to add the minimal structure necessary to solve a problem. Tremendously useful tools of abstraction. But there are some drawbacks to type classes. First off, they're not modular. They're actually anti-modular. Different parts of our code can have their own different ideas about how to order two ints, for example. And that leads to some serious problems. In addition, type class instances are second class. Even though they're values in Scala, it's awkward to treat them as values. Really, it's quite awkward to treat them as values. It's not really intended. And they're not first class in Scala. They're second class, or Haskell. They're second class in Haskell. And you have to use a different set of machinery if you want to do composition and transformation in instances. That's its own programming language, basically embedded in the host programming language. And then, as we saw with many examples, the ergonomics of type classes are imperfect. That's not to say they're terrible. We can learn around them. And once we have, we find it very straightforward. But they really are, in my opinion, they're an obstacle to the widespread adoption of functional programming. Because you just, if you see, I have seen, I've worked with developers who encountered these error messages and ran into that thread that they had to keep on pulling for a really long time before they had a good grasp on everything that was going on. And it's not great. Ideally, I would like them to be productive from day one, rather than having to devote a certain amount of time to self-improvement and self-development, which I hope that they do. I really do. But I would rather we address that right away. And the tools that we have are, or at least the tools I presented in this workshop, are specialize and localize. So take all the names of all your data types and all the operators and constructors and specialize them. And if that means introducing names that merely delegate to type class instances, then do that anyway. Do it anyway. Because first off, developers don't have generic problems, they have specific problems to concrete, tangible pains. So make those names very specific. Don't require they use semi-group append, provide a name that's specific to the domain. Or they I don't know, it's going to vary based on the domain, but like the parser one, the sort of or else, us trying to model alternation in our parser grammars, those are examples of good domain specific names that don't require us to use the domain agnostic machinery provided by type classes. And also localize those names. So put them together with a data type, because that dramatically impacts discoverability. When developers can go there and see all the constructors and all the methods, even if they're just duplicates, even if they're just delegating to other type class instances, doesn't matter. That's going to help them discover that API. Also, inline type classes. So instead of having methods that require type classes, often you can require the set of capabilities that the type class provides. Instead of requiring show, for example, require a string. Or instead of requiring a semi-group, just have the user pass in a function. That technique is very general. There are limits. There are limits because it's not so simple. Like actually, fold left is a great example of deleting a monoid, because you have the empty, that's the start value of your fold, and then you have it's a little complicated to show this, but you have the semi-group append in the other definition. So it's a great example of how that's done. And you know how many developers, at least sort of non-advanced developers, use fold left versus how many use fold map. It's not even close. And imagine if fold map were called something else. Like you can imagine that having even a better, more specialized name that's specific to processing contents of a list in a stateful fashion. And who knows how many more people would use that as opposed to fold left. And then finally, the most powerful technique and tool that I presented here in this talk is using free structures. So free structures allow you to delete a type class requirement and instead provide the result to the user, maybe hide the result if you have to improve ergonomics even further, but provide the result to the user, provide them a free semi-ring or a free monoid or a free monad or free whatever. Provide them a free structure rather than requiring they provide you one of those. That way when they get their concrete data type back from calling your generic code, they can look at its documentation, they can look at the methods, they can see the domain-specific constructors, domain-specific data type, all that can make sense. They don't need to know anything about type classes. All they need to know is how to navigate code and read documentation. And all developers are very, very good at that, regardless of the background, regardless of which paradigm or programming language they come from. They're all very, very good at that. So use free structures whenever you can. The combination of all these techniques are true alternatives to type class based approach, and it can live in harmony with type classes. So what we do in Zio is the data types, they all use these techniques to eliminate type classes wherever possible. And it's almost always possible to completely eliminate the use of type classes. But then also separately, we provide instances for type classes. That means Zio data types may participate in generic code that requires the existence of type class instances. So you get the benefits of both worlds. The discoverability, usability, and ergonomics of Zio is very high. And also, Zio data types may participate in generic code via the traditional type class instances. That's the benefits of both worlds. Now, the drawbacks are obviously it's a different way of thinking about writing software. You have to learn these techniques. And also, it's more work because it's very easy to delegate to the free functionality that type classes provide you with. It's more work to come up with domain-specific names. Even if they just delegate to generic implementations, that's a lot more work. And to localize all these names so that they're co-located with the data type itself, that's a lot of work. So you end up working more in order to provide an API like this. But the end result is that, in my opinion, it ends up being more accessible to developers who are new to functional programming. All right, so if you want to learn more about this, I don't have anything in written form, but I would encourage you to explore the Zio codebase, which uses these techniques extensively, and not just Zio, but many other libraries in the Zio ecosystem, such as Zio config and Caliban, Zio query, Zio test. There are lots of different Zio libraries out there. They are all, to one degree or another, using these techniques to make FP more accessible, but no less principled. That's the beauty of these approaches, is that you don't have to throw away your semi-rings. You just have to call them cause and make them free structures instead of type classes. You can be very principled. You can be rigorously algebraic. Your data structures can satisfy all the right laws. You can ship everything with all the right level of structure and the right requirements. You don't have to necessarily cut corners. You just have to change the way you think about solving these problems. But I challenge you, if you're a functional programmer who has been using the more symbolic approach that is rooted in type classes, then I challenge you to at least stretch your skills, stretch your ability to build code that doesn't sacrifice on its principled compositional algebraic nature, but at the same time is more accessible to developers without a background in any of that. I challenge you to learn that. You don't have to, right? You can keep on doing what you're doing now, but it's nice to know both worlds. It's nice to know how to do it the classic way, as well as to do it the more sort of free structure driven way where we're trying to minimize the background requirements. Both of them are useful. And also I challenge you, if you're a developer who is not familiar with the classic type classes in FP, then, if you have the time, invest in yourself and learn what monads are, learn what semi-rings are, and rings and lattices and functors and monad transformers, category theory. Learn all of that great stuff, because even if you don't necessarily use that day to day, it can still change the way you think about software development. It can force you to look for structure. It can help you understand what algebraic structure is, and it can enable you to identify it in your own business application development. And that can be eye-opening. It can change the way you write software, and it's just good for you. Do things that are good for you. Even if you decide not to take them into a code base, do things that are good for you. And studying algebra and mathematics, category theory, that can be one of those things that are good for you. All right, so I am going to go ahead and stop sharing and open it up for questions. Let's see here.
Okay, thank you so much for that amazing talk, John. I'm always skeptical about this argument we should rename things, and I think you finally figured out how to present it in a way that people can kind of adopt, like this idea that we should have domain specific names. I never really liked, oh, let's rename things to like mappable and appendable and, you know, some other kind of generic name that kind of fits but doesn't usually. I think Elm does this a little bit. But to say that, well, we can keep the same names, but actually in the specific domains in which we're working, solve the specific problems that we have and use names that are friendlier for people who don't care about all of these algebraic structures. This is a compelling argument, the domain specific argument. So this is a kind of good takeaway educational tool for me from this talk. So thanks for that.
Yeah, I think that's a great way to look at it, because you're right. I think some people out there are thinking, oh, well, it's just that functor's a bad name, right? And we can find a single generic name that is better than functor in all cases.
Can't, no.
And that's a never-ending argument. Mappable, whatever, whatever you call it, it's not going to be great. But if you take the more nuanced approach, which is there are many different things that are functors, and what it means to be a functor in one domain is not necessarily the same as it means to be a functor in a different domain. You may be able to, maybe not in the case of functor, but certainly in many cases like semi-group append and even monad and some of the other alternative type classes, you can find names that don't have any meaning in a generic context. Like for each, it has no meaning in a generic context. It would be a nonsense name, but in a specific context, it can make a ton of sense. And that's where I think the sort of domain specific way of thinking about things can make sense. It doesn't necessarily mean you have to forego writing an instance of that type class for your data type, just that you sort of repackage, re-export that functionality in a way that's specific to working in that domain.
Yeah, you're turning the mathematical problem into a business problem without sacrificing the mathematical rigor.
I hope people think about it that way, because I think that's the correct way to think, or at least a useful way to think about that.
Okay, I'm becoming your pitch man. I want to let the the audience ask some questions. So I know that there were a few that were in the chat. Let me scroll back up. So Pad has a question. Pad, can you unmute and ask your question?
Yeah, hi. So can you hear me?
Yes.
Okay. So in the context of Haskell, there's a way to provide some local instances through reflection, with Oleg machinery. And does it make sense in the context of Scala, which I don't know anything of, which has some implicit, but like, would that help, like, kind of, be at the interface of the type class world and still be able to provide? I don't know if it makes sense even in Scala. That's my question.
Scala does have a way to do, actually Scala has always been very strong at doing local type classes, basically. Now, that said, I think there's almost a tension. Like type classes, they really want to be global, because a lot of the benefits, the usability and reasoning benefits of type classes become apparent when they're global. Like if I copy paste this code from one part of my code to another part, or from one scope to another scope, does its meaning change? In general, if its meaning does change, that's a bad thing for code maintenance. And so language features that circumvent that are somewhat problematic in my point of view. And so as a result, I think actually global type class coherence is kind of a good thing, but also it's kind of a bad thing, because sometimes we don't want that. So my own personal preference is to keep type classes for those things which basically, if a data type has very few valid instances of given type class, in particular one is going to be so much more common than any others, I think it really makes sense to use a type class, because then you have one idiomatic way of accessing a set of functionality for that given data type. If like gen is a good example of something that should never have been a type class, then it doesn't make sense. But actually, if you make type classes totally modular, and I don't think anyone's done that entirely, there's more boilerplate to involved, right? Because you've got to supply a local definition and say, oh, in this scope, I want to use this instance, and then other scopes will use their own instance. There's more boilerplate involved. At some point, you're approaching just passing around a dictionary. We're saying passing around a dictionary. We're making it easier maybe to pass around a dictionary when we should just be saying, well, pass around the dictionary. And the other thing is that I think that I think that even in Haskell or Scala, which does really provide good support for this, it's different. It uses a different mechanism, and to have to explain type classes on top of coherence and modularity, and how we work around the sort of global coherence that is otherwise encouraged and adopted by large sections of the Scala and Haskell communities, is another thing to learn. And it's another list of exceptions to exceptions of rules and so forth that you just have to teach. And even though it's appropriate for more advanced functional programmers, I think it presents yet another obstacle. If we have ways of making type classes, I'm actually in favor of deleting the ability to have incoherent type classes, just because it makes things simpler and it makes it clear when to use a type class and when not to, rather than expanding the ways in which we can use type classes. That's my own personal preference, though.
Okay, if there's no follow-up, then Barisare Jonathan has a question, if you would like to unmute. Barisare, are you there? I can ask your question for you if necessary. Okay, I suppose I will ask it then. He says, I've seen John change his mind on breaking the principles sometimes. He got some flack some time ago when he suggested that we could break the rules if it's worth it to get more people in. How did you change your mind?
Yeah, so here's one example. Originally, I was of the opinion that all instances of a type class for a given data type should satisfy the laws. But then over time, I have come to appreciate the benefits of taking a more relaxed approach on that. And I'll give you an example. Float and double. Our friends, float and double, and also int and long, they actually don't satisfy any law, any reasonable laws in math anyway, in abstract algebra. And the reason is IEEE, and also finite memory. There's a whole host of reasons that these laws are not satisfied, they're violated. But the reality is that they are satisfied in many cases enough to be interesting. So what I mean by that is, if you do not provide semigroup and monoid instances for int and long and float and double and so forth, then users will not be able to use generic code that will usually work or work well enough in practice to solve the problem that they have. And as a result, people end up defining orphan instances, or they end up duplicating generic code that would work in their case. It just wouldn't provide the same level of guarantees. So basically, the older approach that I had, in my opinion, it was too preachy. It was too preachy. It's like, don't define these instances because they're not lawful. Well, I understand that, because ultimately we only know the meaning of generic code is well defined if the instances for our data types satisfy all the algebraic laws. But nonetheless, in many cases, if the combine operation we're providing to fold map is not associative, for example, it still gives us an answer. And that answer is oftentimes the very same one we're looking for. And especially with the semigroup and monoid instances for all the numeric types, which don't satisfy the laws, still that we go into that understanding that we're working with fixed types that are imprecise, that have rounding errors, that don't consume all memory. We can actually lose information, overflow and underflow. We go into it knowing that these types we're working with have these properties. And so accepting a sort of graceful degradation where we can call the generic code, even if it doesn't satisfy the laws, we just don't get the same guarantees. That's what it is, right? It's not being preachy and saying it's okay to call generic code even if you don't satisfy the laws, just so long as you know that what you're getting back might not be as principled and as well-founded as it would have been if your data type had actually satisfied the laws. And I think that that approach, it makes FP more useful, because what everyone was doing is they were defining orphan instances for their own data types, or they were not checking laws for their own data types, and they were still calling the same generic code. So nowadays, my philosophy is provide all the instances that people are going to define anyway, even if you leave them out. Like, allow them to cheat and break the rules if they need to. As long as they understand the guarantees that they get back out of that generic code are necessarily going to be weaker. Don't be preachy. Help the programmer solve the problems they have, even if they choose not to solve them in a principled way. They can still use BigInt or big decimal. If they want things to be satisfied, just don't be preachy. Let them use float and int too, because in many cases, they're willing to accept the trade-offs that come from doing so.
Pragmatism versus purity, the ultimate battle in the FP world.
It is, it really is. It's a big age-old battle that I don't expect we'll solve tonight.
Okay, we have a question from our mutual friend, Harold.
Hey.
Hey, how's it going?
Good. Oh, LambdaConf, yes, awesome.
Yeah, there it is. And actually, I forgot about your presentation today. I just had this on because.
Oh, wow. Fate.
That's like wearing the shirt of the band you're going to see, you know.
Exactly.
That's one of my favorite
anyway.
Our favorite editions.
I was wondering how you felt about domain-specific records of functions in place of type classes.
I like that. I like that. And I think like gen is a really, well, sort of gen is like, it could be viewed as a record that provides capabilities of generating A's. That's very domain specific. I think I like that. I think it makes a lot of sense. It's related to executable encoding and functional design, basically, where you model a given domain as a bunch of functions. And these functions may satisfy relationships and laws, but fundamentally all you have there is a record of functions.
Right, okay. I know when I first started in functional programming, and this is kind of to your point about education, I wanted to do it the right way, whatever that meant. And I couldn't decide whether type classes or records or function was the right way. Yeah, so it's an issue.
Yeah, it is. I think that's an interesting question. How do you decide when to type class and when not to? That's an interesting question. But anyway, if you buy the gist of this talk, then in any case where you could solve the same problem with and without type classes, you would solve it without introducing a new type class, because then you wouldn't have to work around the type class with all these other techniques that I was teaching today.
Right. The only trouble with records is that it gets, you get back to the boilerplate problem again.
Right. Yeah. And that's the addictive part of type classes is right. It stops you from passing around a parameter manually, which has maybe led to some type class abuse, unfortunately.
Right. But then you have template Haskell to solve it.
Yeah. But then you have holy wars on that. Half of our audience today probably hates template Haskell and would never use anything, and the other half loves it. It's weird. Good question. Yeah, good to see you, Harold.
Thanks, Harold. Frequent visitor to our meetups, Ulrich, has a question that I'm a little worried about it. I think you may be breaking the hearts of many diehard Haskellers with this answer.
I thought it was just a very, very short, quick question from what I heard you saying. I suppose you're also not a big fan of complex symbols for operators instead of function names?
Right. And so I'm very torn on this because me personally, the mathematician in me, I want the symbols. I want the operator. I want them. In fact, I want them to be Unicode. But unfortunately, this is one area where I have to, like, if ultimately my goal is not necessarily to write pretty code, and unfortunately I have that goal, I want my code to be pretty. I align all my parentheses and I use all the operators when I can, and I try to make everything very pretty because aesthetics matter to me. But also my number one goal actually is just helping the world at large discover the value that functional programming has to improving the way the commercial sector develops software and maintains software. And so that's number one. And I have to acknowledge that despite the fact that I love operators, symbolic operators, they have a negative effect on discoverability and on communication and education and searchability. And of course they can't be pronounced. So what do they mean? Well, you have to it's easy to for us functional programmers to understand them through their laws, their algebraic laws. That's a different way of thinking that has to be taught and learned to people outside the FP community. So for all of these reasons, I think we have to, at the very least, minimize the number of symbolic operators that we have. And number two, we should never have a symbolic operator that does not also have a name that is, as specific as the context warrants, ideally domain specific, to that given problem domain. And if you follow that's what we try to do in Zio. Zio does have some symbolic operators, maybe too many actually, but for every single symbolic operator it also has a name, and that name tries to be as domain specific as possible. And I think that's a reasonable trade-off. If you don't want to totally give up the symbolic operators, and who does, right? They're so too beautiful to give up entirely, but they're just not good. Developers hate them. Like developers from Java, they hate them. They can't search them. They can't pronounce them. They don't know what it is they do because the name provides no hint. They're not good for FP adoption.
All right, thanks.
Yeah, I love the operators, but they're clearly some kind of form of gatekeeping, and I think they promote a bit of condescension too, right? I can read the code and you can't.
Yeah, and even though I don't think we intend them that way, unfortunately, that's just how they're seen, and we need to face that. Like, we can admit that we like them, because I have no problem doing that. I love them, but also admit that they are a problem.
Yeah, and the proselytizing doesn't work. You try to explain, no, don't you understand? This is a binary operation. It completely makes sense that we want an operator here, a symbolic operator, because it's this common abstract pattern, and here's how it relates to other kinds of algebras. It just whoosh.
Yeah, and at some point you need to decide if you want to spend your days preaching or spend your days growing FP. And you grow FP, I think, more effectively. I'm not sure, but I think you grow FP more effectively by just adapting to how people are rather than trying to change who they are.
Yeah, I mean, unfortunately, getting into FP seems to entail this like preaching period that you go through because you get so excited about it.
I know.
You start preaching, basically.
Yes.
How did you put it once? Rediscovering the magic of programming. I mean, this is exactly what it was for me. I could never convince anyone of anything, though, when I tried to talk about like abstract things that were not problem specific.
Yeah, it's an uphill battle.
Okay, we have another question from Alexandra. Alexandre? I don't know how to pronounce that.
Anyway, it's fine. So you talked about modularity and locality, and I see people who talks about event handlers talking about those sort of things as well. So I was curious if there is any relationship between the two things.
Well, I think that
I misspoke. I said event handlers as I meant effect handlers.
Right. I think that the meaning of modularity there is similar. Basically, modularity is a measure of the extent to which solutions can be expressed requiring only the concerns that they themselves are interested in. If a solution has to tangle two concerns for architectural reasons, not because it wants to tangle them or it needs to tangle them, but if it has to tangle two concerns for architectural reasons, then it's anti-modular. And in effect systems, one of the goals of a modular effect system is to be able to say that the part of code here that introduces this effect knows how to resolve it, how to handle it, how to eliminate it, and other parts don't need to know about that. So modularity in effect systems is a good design goal. And then also modularity in abstraction is a good design goal as well, because we want this code over here that wants to be able to say how two integers are ordered, what it means for one integer to come before another, to be able to have its own local notion of that without tangling what it needs with what this other area of the application over here needs, which might be a different notion of which integer comes before which integer. So modularity, it's the same definition of modularity in both cases. And modularity always, in my opinion, like a good definition for modularity is always about detangling things and making sure that when we write code, it knows only what it needs to be able to know about in order to solve the problem. It doesn't have to tangle in unrelated concerns from other parts of the application, whether you're talking about effect systems or type classes abstraction.
Okay, if there's no follow-up, there are no further questions. And actually, it's starting to get a bit late in Berlin anyway. So just want to thank you again for a great talk. I just realized it's the 100th meetup event for this meetup group. Not the 100th virtual talk, but the 100th event. And we even almost reached 100 participants at one point. So I would call that a success. John, thanks again for joining us. If you'll stick around for a few minutes, maybe we can catch up quickly.
Yeah, that'd be great. I will do that.
I'm going to stop the video now. Thanks everyone for your questions and thanks for joining.
Thank you, everyone.